The aim of this lecture is to introduce the notion of Gaussian measures on Banach spaces. On previous two lectures, we looked at Gaussian measures in n-dimensional space. Today, we will define what is a Gaussian measure on a general Banach space. My setting will be the following. X is a separable Banach space. B of x is a Borel sigma field in X, and we will consider probability measures on X, on Borel sigma field of X. The definition we give is just copy-pasted from finite dimensional case. However, the probability measure will be called Gaussian if all linear continuous functionals on X are distributed as Gaussian random variables with respect to the measure gamma. In other words, for every linear continuous functional on X, the image of measure gamma under this functional is a Gaussian probability measure on the real line. The difference with the finite dimensional case is that in finite dimensional case, all linear functionals are continuous, while in general it is not true. So here we impose the condition that L must be continuous. Equivalent definition, if we recall what is a Gaussian probability measure on the real line, can be given as follows. So a probability measure is Gaussian if there is some linear function A on the dual space and some symmetric bilinear non-negative function F. Okay, so this is a function of two functionals such that for every linear continuous functional L, the Fourier transform of gamma of L, which is defined like the integral of exponent ILX d gamma x, equals to exponent of IA of L minus 1/2 f of L and L. So this is indeed an equivalent definition. Let's check this. So assume that gamma is a Gaussian measure, then we can just guess what must be A and what must be F. So A of L, this is just the mean value of L, of the functional L with respect to gamma. And F, L, and G is the covariance of functionals L and G with respect to measure gamma. So we integrate the product and subtract mean value from each function. Then, of course, A is linear, F is symmetric, bilinear, and non-negative. Actually, F of L and L is a variance of functional L with respect to measure gamma. Now if we compute the Fourier transform of gamma, we will get the following. So the Fourier transform, this is the integral of exponent I L of x d gamma x. But this is the same as to integrate over the real line E I t with respect to the image measure, which we know is Gaussian. So the Fourier transform of gamma at L, it is the same as the Fourier transform of the image measure at point 1. And we know what it is. It is exponent I times 1 times the mean value, which is A of L. This minus 1/2. Again, t is equal to 1, argument is equal to 1. And here must be the variance of L, which is f of L. So we obtained the needed representation of Fourier transform. Conversely, if such A and F exist, then we check that all linear continuous functionals have a Gaussian distribution. The Fourier transform of the distribution of L at point t, so it is equal to the integral of E, let's say I, T, S, with respect to the image measure, and by definition of the image measure, this is the integral over x, E, I, T, L of x. So we obtained the Fourier transform of gamma for the functional TL. And since A is linear and F is bilinear, we can take T out of A and T squared out of F, and we get the characteristic function of a Gaussian measure. In this expression, for the Fourier transform, A of L is, as we saw, this is the integral of over x, L of x d gamma x. In the finite dimensional case, we wrote it in a bit different way. So we wrote it's like L in a product with some vector A. And actually, vector A was the integral of x1, x2, xn with respect to the measure. So it is expected that here we will also, instead of A of L, will be able to write L of A. Meaning that this is a linear functional of some vector of the space, and call this vector a mean vector of Gaussian measure. However, it is not obvious that such vector exists, because now A it is a linear functional on the dual space. Of course, in some cases, it is easy to prove that this functional has exactly this form. Well, here is some ambiguous notation. So if a vector exists, I will denote it also by A. Well, for example, if this functional is continuous and the the space X is reflexive, then A is an element of the second dual, but second dual coincides with X. Yeah, so in this case, such vector A exists. But actually, we can prove it in general. So the theorem is that for any Gaussian measure, there exists a unique element A in X such that L of A is exactly the mean value of functional L with respect to the measure gamma. Uh, such such type of integration. So here we integrate the function that takes values in the Banach space. So if there exists a vector A with this property, then A is called the integral of x d gamma x in the sense of Petit's. So this type of integration is called Petit's integration. So now let's check that indeed the mean vector exists. For this, I will need a lemma. So let P be greater or equal to 1. We know that Gaussian measures on the real line, they have all moments. In particular, since linear continuous functional has a Gaussian distribution, it means that it can be viewed as an element of all spaces LP. That is, we can embed the space of linear continuous functionals into any LP just by mapping L into L. So this lemma tells that this embedding is actually continuous. So the LP norm of linear continuous functional can be estimated by some constant times its norm as in the space of linear functionals. Maybe I should recall that norm of L is a supremum L of x over norm of x when x is not 0. Yeah, so this is the norm in the dual space. So such estimate holds. And this follows from the closed graph theorem. So here, the domain and the range of an operator, they are Banach spaces. So if a linear operator is defined on the whole space, and if it is closed, then it is bounded. Closed operator means that if we have a convergence of vectors, in our case, functionals converge, it is enough to consider convergence to 0 in the dual space, and their images converge somewhere in LP. Then this limit f must be equal to 0 in LP. Then it means that the operator is closed, hence it will be continuous. But this is actually easy to check. So now TLN is just Ln. So if Ln converges to f in LP, then we can choose a subsequence that converges to f almost surely. But also this subsequence will be pointwise convergent to 0, because we have this estimate. So we have that f is an almost surely limit of functions that pointwise converge to 0. This means that f is equal to 0 almost surely. Okay, so operator is closed and bounded. So now let's construct the mean of measure gamma. The idea is to first to construct the integral over bounded sets. For example, consider the ball B of vectors that are norm of which are less than n. Since the space X is a separable space, so we can split the set B into sets of diameter less than 2 to the power minus k. This can be done as follows. We consider dense countable set and take a neighborhood of each point of small enough radius if these neighborhoods intersect, we can make them disjoint. Okay, and we will obtain actually a countable partition of B. And if we take a large enough number of sets from this partition, the rest part will have a small measure gamma. So it follows that we can find a partition A0 to A sum m such that the measure of A0, this is like the small part that remains, is less than 2 to the power minus k, and the diameters of sets A1 to AM are also less than 2 to the power minus k. And let's pick a point from all sets of this partition, and let's agree that x0 is 0. And now consider the function fk, which on each set of partition takes the value xg. Then if we estimate the norm of the difference of x and fkx, you can think of fk as a simple function which easy to integrate. Then if x belongs to, let's say, a1, then this will be the norm of x minus x1. but the diameter of A1 is less than 2 to the power minus k, so we get this estimate. And same holds for all sets A1 to AM. And if x belongs to A0, then we just have norm of x, which is less than n. Okay, so, but the measure of A0 is less than 2 minus k. So when we integrate over A0, we get this term. And when we integrate over all other sets A1 to AM, we just integrate the function which is bounded by 2 to the power minus k. Thus, we have this estimate, and in the limit, it gives 0 when k goes to infinity. Okay, and now let's integrate the function fk. Consider the following element in x. This is the sum of vectors xj times measures gamma of aj. Then yk is really the integral of function fk of x as an integral of function with values in Banach space. Because when we apply some functional to yk, we get the sum of lxj gamma aj. But on the set aj, function fk is equal to xj. So this is the same as the integral of Lf of k of x d gamma x. This equality implies that if we apply some functional to the difference yk minus yr, then this is equal to the less or equal integral of b L applied to fk of x minus fr of x, absolute value d gamma x. So then we can estimate it as the norm of L times the norm of the difference. But recall that integral of fk of x minus x converges to 0. This means that, no, it's too early. I recall that for Banach spaces, there is a dual formula for the norm of the vector. The norm of the vector can be also computed as supremum of L of y divided by norm of L when L is not equal to 0. This is a consequence of Hahn-Banach theorem. So if we obtained such an estimate, then we actually estimated the norm of yk minus yr. And the norm of yk minus y, it must be r, yr, less than the integral of the difference fk minus fr, which converges to 0. So this means that yk is a Cauchy sequence, hence it has a limit an. And if we integrate if we apply a functional L to an, then we get the following value: the limit of integrals of L fkx d gamma x. But these integrals, in turn, they converge to the integral of L of x. In other words, we obtained an element an such that every linear continuous functional acts on an like the integration of L of x over the ball of radius n. We can say that an is the integral of x d gamma x over the ball. So here the essential thing is that the ball is bounded. Okay, and you can guess what we will do next. We will prove that an converge, and their limit will be the needed mean value. L of an minus am. This is the integral of this form, but the integral over the set, if n less than m, the integral over the set n less norm x less or equal to m. We can estimate it as by Gaussian inequality. So as the L2 norm of L times the root of measure gamma of this set. And now recall the lemma that L2 norm is estimated by some constant times the norm of L as a functional. And since the estimate holds for all linear functionals, again, we deduce that actually we estimated the norm of the difference. And it is estimated by a quantity that converges to 0 when n goes to infinity. So the limit of an exists, and applying linear continuous functional to this limit a, we just get the integral of L of x d gamma x. So for any Gaussian measure on a separable Banach space, the mean value exists. By the way, one can define in the same way one can define Gaussian measures in non-separable Banach spaces, even in a so-called locally convex topological linear spaces, and there this result is not true already. So some additional assumptions are needed for the mean to exist. As an exercise, I leave absolutely analogous result. Recall the bilinear form, this form, which we denoted by f. Actually, it can be written also like this, because we know that the mean value exists, and if we integrate just Lx minus LL, we will get 0. Okay. Now this bilinear form can be understood as a mapping, again, from the dual space into the second dual space. If we consider it for fixed L, we can consider it as a function of second argument, and then we will get the linear functional on the dual space. In this way, it can be considered as a linear mapping from dual to second dual. Actually, this the value of this mapping is also belongs to X, not to the second dual. All right. And actually this value is the integral of Lx minus a x d gamma x. The existence of this integral is proved absolutely along the same lines we did it for the mean value. So we can summarize and give another definition of a Gaussian measure. So a measure is Gaussian if there is some vector A and some bounded linear operator R, which is symmetric in the following sense, non-negative in the following sense, and for all L, we have that Fourier transform of gamma is equal to exponent IL of A minus 1/2 L RL. By the way, one can also check that this operator is bounded, which again follows from the lemma where we estimated LP norms by the norms in this space of functionals. So A is the mean value, and R is the covariance operator. Now I introduce some important spaces. So X star gamma is the closure of the set of functionals in L2. Here we subtract the mean value from every functional and take the closure of this set. The covariance operator can be also defined on the closure, and it is defined as the integral of f of x x d gamma x, meaning that if we apply a functional g on this element, we will get the integral of f of x g of x d gamma x. We can subtract mean or don't subtract mean. It is not important because the integral of f is 0. So we extend the action of covariance operator on space X star. And now I introduce the so-called reproducing kernel Hilbert space or Cameron-Martin space. This is a set of vectors in the Banach space for which the so-called Cameron-Martin norm is finite. Cameron-Martin norm is defined as a supremum of L of H over all functionals such that LRL is less or equal to 1. I remind that LRL is equal to the integral of L of x minus a squared d gamma x. Okay, so the Cameron-Martin space contains precisely vectors for which such norm is finite. And we will see that this space plays a very important role for a Gaussian measure gamma. In fact, it turns out that this space exactly coincides with the range of R when we consider it on the space X star. In other words, the Cameron-Martin space consists of all integrals of this form, integral f of x, x d gamma x, and such that f is in the closure of linear functionals in L2. Okay, so let's prove it. Assume that H belongs to the range of the covariance operator R. It means that H is equal to the integral of f of x, x d gamma x for some function f. Then if we apply a linear functional L to H, we just apply it under the integral on x and use the Gaussian inequality. So this will be less or equal than norm f in L2 times the variance of functional L. So if we take now this less or equal to 1, the supremum of LH will be bounded. Okay. Now, conversely, consider an element from this Cameron-Martin space. So now let M be linear functionals. Centered linear functionals, so that the space X star is the closure of M. And now let's consider L of H as a function of the centered functional L minus LA. We have an estimate. Here must be square root. We have an estimate that LH is less or equal some constant times root of the variance of L. This is how we define elements in the Cameron-Martin space. One has to check that functional f is well defined, meaning that this difference, if we consider it as an element of L2, then we consider it up to the sets of measure 0. And it can happen that this difference is 0 almost surely. But then it has a 0 variance, and we get that L of H will be also 0. So f is well defined and bounded. If we have a bounded functional on the dense space, it can be uniquely extended to a continuous linear functional on the whole space. So f can be extended to the space x star, and since this is a Hilbert space, f is defined by some element from x star. L of h, which is the same as f of L minus L of A, must be equal to the inner product in L2 of this function and some element of x star. That is, we represented h as the value of the covariance operator. Okay, so this is an important result, that the Cameron-Martin space of the Gaussian measure coincides with the image of the covariance operator, but not of the space of linear functionals, but its closure in L2. Every element of this closure is a centered Gaussian random variable, and its variance is equal to the norm of g squared, norm in L2. So every function g is a limit in L2 of differences ln minus ln of a. We just compute the Fourier transform of the distribution of g. So this is a limit. This is a limit of such integrals. Here we subtract a mean, so we get the Fourier transform of gamma of ln, but minus its mean, which is equal to exponent minus 1/2 t squared ln r ln. But this quantity, it is exactly the L2 norm of ln minus ln of a squared. And it converges to the norm of g squared. Now I will give some examples, and at first I introduce the very special Gaussian measure on the space of all sequences of real numbers. This space is denoted by R infinity. The metric on this space can be defined as such sum 2 to the power minus n, the minimum of differences of components, and 1. As an exercise, I leave for you to check that in such a way we get a complete separable metric space. Convergence in this space is equivalent to coordinate-wise convergence. So sequences xk converge to the sequence x if and only if each component of xk converges to the corresponding component of x. Also, if we add two sequences, it will be a continuous operation. If we multiply a sequence by a number, it will be also a continuous operation. And also, the Borel sigma field in this space is actually the cylindrical sigma field. In other words, the Borel sigma field is the smallest sigma field under which all coordinate functions are measurable. However, R infinity, it is not a Banach space. So there is no norm on the space of all sequences that will give the equivalent convergent to the coordinate-wise convergence. So this is not a Banach space. It is the so-called Fréchet space. However, it also has a linear structure. It has the notion of convergence. So we can define a Gaussian measures on this space as well. And by gamma infinity, I will denote the probability measure, which is actually the product of one-dimensional Gaussian measures. This is the measure gamma infinity. It is the distribution of a sequence of standard Gaussian random variables, independent standard Gaussian random variables. Okay. Let's find all continuous linear functionals on R infinity. In fact, all continuous linear functionals have such a representation. So the action of the functional on the sequence is the sum of some coefficients times the components of this sequence. And moreover, for all large enough n, coefficients Ln are equal to 0. In particular, for every sequence, this sum makes sense. All right. Assume that we have a linear and continuous functional. Since it is continuous, then L is bounded in some neighborhood of 0. Let's say when the distance from x to 0 less than some alpha, then f is bounded, let's say, by 1. Not f, but L. The distance from x to 0 is the sum 2 to the power minus n minimum of xn and 1. And if we split it into 2 parts, from 1 to some large n, and from large n plus 1 to infinity, in the second sum, I estimate minimum by 1. Then if we choose n large enough, this can be done. This can be made as small as possible. I mean, as small as needed. And then we can choose xn from 1 to n to large n, again, small enough to make this expression less than alpha. This means that if there exists some large n and epsilon such that if x1, xn are less than epsilon, then the functional L of x will be less or equal to 1. If x1, xn is equal to 0, then for any multiple here, we'll have that cx1 less epsilon, cxn less epsilon. This means that L of x will be less than 1 over c. And increasing c to infinity, we deduce that if the first 10 components are equal to 0, then the functional is also equal to 0. It means that if we take some sequence x, subtract first n components, we will get 0. And the functional will be equal to 0. So what remains is the action of L on such sequence x1 to xn, and then 0, 0, and so on. Such sequence can be written as a linear combination of sequences en. Hence, we get such a representation for the function. Okay. And so we can compute the Fourier transform of this measure gamma infinity, and it will be equal to exponent minus 1/2 sum of ln squared, where L is a linear continuous functional on R infinity. Again, this series converges because actually only finite number of coefficients ln are not equal to 0. This measure can be also considered as a measure on some Hilbert space. For example, if we have a sequence of positive numbers, alpha, which is squared convergent, we can consider sequences for which the sum of alpha squared x squared is finite. Then this space will be a Hilbert space with respect to the following inner product. So the inner product of two sequences is defined as the sum of a product of their components and coefficients alpha squared. Then actually the measure gamma infinity is concentrated on this space. This is a consequence of convergence of alpha. This series is convergent, and we can represent it as sum of alpha squared times the integral of xn squared. Because this integral is 1, this is finite. If we interchange sum and integration, we obtain that for almost all x, the series is convergent. Which means that the measure gamma infinity is concentrated on E alpha, so it can be also viewed as a Gaussian measure on Hilbert space. Let's find the covariance operator of this measure. It is found easily, so we integrate the product yx and zx, d gamma infinity of x. And since coordinates of x are distributed as a standard Gaussian variables, we will obtain the sum alpha n to the power 4 yn zn. And then we can find the Cameron-Martin space of this measure, and it will be L2. So we need to find out for which sequences Hn such supremum is finite. Note that if Hn is in L2, then we estimate the sum by Cauchy inequality. It will be the sum alpha n to the power of 4 xn squared square root times the norm of H in L2. And this is less or equal to 1. So if H is in L2, then the supremum is finite. The converse is also true. Let this supremum be equal to C. Consider such vector, consider such sequence x1 is h1 divided by alpha 1 squared, and let me denote by dn. It will be the sum of first n squares of h square root, and I define xn as hn divided by alpha 1 squared dn. This is until xn. And then xn will be equal to 0. Now, if we compute the sum of alpha n to the power of 4 xn squared, we will get actually the sum from 1 to n, and it will be the sum of hk squared divided by dn squared. But this is 1. This means that if we now compute the sum alpha k squared xk hk, it will be less or equal to c. But this sum is equal to dn. So all sums of hk squared from 1 to n, they are bounded, which means that h belongs to L2. Okay. So what we did, we first we defined the measure gamma infinity on the space of all sequences. Then we showed that it is concentrated on some Hilbert space of sequences, and found its Cameron-Martin space, which is actually L2. And it is an interesting fact that the measure gamma infinity of L2 is equal to 0, because the sum of squares of independent identically distributed random variables cannot converge. So later we will see that, as I already said, that this space is very important for the measure. However, the measure of this space is 0. And one more example. Fix some positive numbers, sigma 1, sigma 2, and so on, and multiply every sequence by correspondingly sigma 1, sigma 2, and so on in every component. And gamma sigma is the image of measure gamma infinity with respect to this mapping. This means that under the measure gamma sigma, components are independent, but they have independent Gaussian random variables that have expectation 0, and nth component has variance sigma n squared. It turns out that this measure is concentrated on the space L infinity of bounded sequences, if and only if such series converges for some epsilon. Now we will quickly discuss this result, and also as an exercise, I leave for you to show that if the series converges for any epsilon, then this measure is concentrated on the space C0. This is the space of sequences that converge to 0. In particular, we obtain necessary and sufficient conditions when the sequence of independent centered Gaussian random variables is bounded almost surely, or convergent to 0 almost surely. Okay, so now the proof of the first fact is follows from this estimate, which is a well-known. And in fact, the proof of the second statement follows from the first statement. Now, if we apply the estimate to the measure of complement of a segment from minus r to r. So this measure is root of 2 pi integral from r over sigma n to infinity e minus z square over 2 dz. Then we get this two-sided estimate. Okay. Now let's find the complement of set of sequences that are bounded by R. So this is actually, the unit ball in the space of bounded sequences. So if a sequence is not in this set, then there is some component which is bigger than R in absolute value. So this complement can be estimated by the sum of measures of complements of segments. And we estimated this measure as sigma n over r exponent minus r squared divided by 2 sigma n squared. Now, when r converges to infinity, each term of the sum converges to 0. And also we have the condition that for some epsilon, the series of exponent with epsilon converges. So by dominated convergence, this converges to 0. In particular, now when we take the limit in the left side, we get the union of balls in space of bounded sequences. So we will get the whole space of bounded sequences, and its measure will be equal to 1. Okay, and conversely, it's actually similar. If the measure is concentrated on the space of bounded sequences, then some ball in this space has a positive measure, which is such infinite product. And infinite product converges if and only if such sum converges. And if now we use the second estimate, this one, so here cube is sigma n over r cube is not important since sigma n converges to 0. So we will get the convergence of this series. And actually, we can remove also sigma n by slightly decreasing this multiple, which means that for large enough epsilon, the sum of exponents minus epsilon over 2 sigma n squared will be finite. Okay, and next time we will have more examples of Gaussian measures. And thank you for the attention. If you have questions, please. Okay, then see you next week.
Bye bye.